Imagine trying to have a conversation across a crowded room. Your voice doesn't travel directly to the other person. It moves through the air, mixes with background noise, reflects off walls, and gradually becomes weaker. Wireless signals experience the same challenges. The path between a transmitter and a receiver is called the communication channel, and it is one of the most important concepts in communication engineering. In the previous lesson, we learned that communication systems use either analog or digital signals to represent information. However, generating a signal is only the first step. Once the transmitter sends it, the signal must somehow reach the receiver. If communication occurred in a perfect world, the transmitted signal would arrive unchanged. Unfortunately, real communication channels are far from perfect. Signals become weaker with distance, reflections create multiple propagation paths, noise is added from the environment, and interference from other transmitters may distort the information. This creates one of the biggest challenges in communication engineering. How can information survive an imperfect transmission path and still be recovered accurately by the receiver? The answer begins with understanding the communication channel. A communication channel is the physical medium through which information travels from a transmitter to a receiver. The channel can take many different forms. It may be free space for wireless communication, a coaxial cable, an optical fiber, or even a pair of copper wires. Regardless of the medium, the channel carries the transmitted signal while simultaneously introducing various imperfections. An ideal channel would deliver the signal without any changes. A real channel, however, modifies the signal by introducing attenuation, delay, distortion, noise, interference, and sometimes complete signal blockage. Understanding these effects allows engineers to design systems that remain reliable under real operating conditions. Intuitively, a communication channel is like a road connecting two cities. The transmitter loads information onto a vehicle, and the receiver unloads it at the destination. A smooth highway allows efficient travel, while traffic, construction, and bad weather slow the journey and increase the chance of problems. Physically, consider a Wi-Fi router communicating with a laptop. The electromagnetic wave leaves the transmitting antenna and propagates through the air. Along the way, walls absorb part of the signal, furniture reflects it, people scatter the waves, and other Wi-Fi devices create interference. By the time the signal reaches the receiver, it is no longer identical to the one that was originally transmitted. Mathematically, engineers often model the communication channel as a system that transforms the transmitted signal into a modified version. This model helps predict attenuation, delay, and distortion, allowing receivers to compensate for many channel impairments. Communication channels are central to RF engineering because they determine the overall performance of every wireless system. Whether designing cellular networks, satellite links, Bluetooth devices, radar systems, or IoT sensors, engineers must understand how the channel affects signal quality. Different environments produce different channel characteristics. Indoor channels experience strong reflections from walls and furniture. Urban environments introduce multipath propagation between buildings. Satellite channels involve long propagation distances, but fewer nearby reflections. Fiber optic channels exhibit entirely different behaviors compared to wireless RF channels. At the system level, channel analysis influences transmitter power, antenna placement, modulation schemes, coding techniques, receiver design, and communication reliability. A well-designed system always takes the channel into account. The communication channel is often the greatest source of uncertainty in an RF system. While engineers can carefully design transmitters and receivers, they usually have much less control over the environment through which the signal must travel. A common misconception is that communication failures are caused only by poor transmitter or receiver design. In reality, many problems originate in the channel itself, where attenuation, reflections, interference, and environmental changes degrade the transmitted signal. Among all channel impairments, one appears in every communication system regardless of the transmission medium: noise. In the next lesson, we will explore noise in communication and discover why random electrical noise fundamentally limits the performance of every communication system. In this lesson, we learned that the communication channel is the physical medium that carries information from the transmitter to the receiver. We also saw how real channels introduce attenuation, reflections, distortion, interference, and other effects that change the transmitted signal before it reaches its destination. In the next lesson, we will explore noise in communication and discover why every communication system must deal with random noise and its impact on signal quality. If you found this useful, like the video, subscribe, and follow for the next lesson.